Welcome back to the next topic that we are going to discuss, and this is lies at the heart of the continuous time finance theory, which is what is called as stochastic calculus. Okay. So, basically what we would define what is called as an Ito integral and analyze their properties that leads to the famous formula called as Ito formula that lies at the heart of all the calculations that you do in stochastic calculus. And then we talk about a little bit about other things about its applications, right? And the calculus is basically based on the Ito's formula, which is you can make a analogy with the ordinary calculus formulas. Yes. Okay. So, anyway, let us start. So, basically what we want to do first is basically the what we call as Ito's integral, and first what we will consider is basically Ito's integral for simple integrands. Okay. Later we will generalize to a more general integrands under certain assumptions. Okay. So, basically what we want to see is we want to make sense of a quantity of something like this. As I said, delta of t, I am writing it as delta in the suffix t, and similarly for the w. So, the basic ingredients here are, you have a Brownian motion process, right, along with filtration for the Brownian motion. When we say filtration for Brownian motion, then you know what it means exactly in per definition, and you have a process delta t which is adapted to this filtration. Again, since this is a Brownian motion for this is a delta t is adapted to ft, and ft is a filtration for the Brownian motion, right. So, we mean that by time t, the value of delta t should be determinable. I mean, when you go forward, you would see this is would be similar, or this also represents, among other things, one of the quantities that which will denote our positions in the underlying stocks, okay, which are all will be adapted process as we said earlier. And since this is a Brownian motion for ft is a filtration for the Brownian motion, even this delta t should give no clue about what is going to be your wt. Okay. That is what we will keep that in mind. You may recall that this integral is something like in the ordinary calculus that you might encounter, and you may see that as I digress, you can see, suppose if I look at some integral, okay, of some function of t and dg of t, say I will write it here in this form. So, maybe this also I will write it in this form, okay. And if g is differentiable, this is equal to 0 to t delta of t g dash of t dt, if g is differentiable, and the right hand side is nothing but your ordinary Lebesgue integral or Riemann integral, when both are exist, then one and the same. So, this is what would mean. But here look at this function wt is a non-differentiable function, right. That is where the problem comes, that this cannot be defined in this manner as one does in the ordinary calculus theory, and hence we need to have a different way to give a meaning to this quantity, which is what will keep occurring in stochastic calculus, where the integral where this function g in the ordinary calculus that you look for So this is will be taken by this W, but the paths of this Brownian motion are nowhere differentiable. Okay. So that's where the things will come. Now let us look at the construction, how we can construct such an integral, construction of the integral. So what we have, so what this construction is, what was done by Ito, right, who devised a way to give meaning to such an integral in the following way around the non-differentiability of the Brownian paths. Okay. So we first define, as we said, for the simple integrands, then we consider and are extend it to non-simple integrands as a limit of integral of simple integrand. So and hence the understanding that we require in understanding the basic integral in terms of the simple integrand is crucial, and hence I would suggest that you spend some time in understanding so that the meaning is clear what exactly we mean. Okay. So let us take as usual, we have an interval, okay, of 0 to t, and you take a partition of this interval, say t naught, t1 and so on tn, such that your 0 is your t naught and t1, t2 and so on are all the other points in the partition, and we also assume delta t is constant with respect to t on each sub interval, which is tj to tj plus 1. Such a process is what we call it as, such a process is called simple process. Okay. Right. So if I look at how this will look like, okay. So if I take this, now what this is, so this is along the x axis you have the time, and along the y axis you have your delta t, which might be even this. Okay. So what this says is that at time 0, which is t naught here, this is 0, and this is say t1, this is t2, and this is t3, suppose if this is the case, and so one more thing, so this is t4. Okay. So what this says is that delta t is constant in each sub interval. So between 0, which is what is my t naught, and t1, this is constant. Okay. So you take the position starting at t and hold it until up to t1, but not t1, just before t1, until that. Okay. So which is what this position would be. Then at t1, you may change your position to here, and then until t2 you may hold it, and at t2 it could be any position, so even it can take negative values. So at t2 you have this, and until up to t3, and at t4 you hold take this value, and then until up to t4, and then from t4 it is starting. So it is, if you look at as a simple, without looking at the bringing in the stochasticity in mind, this is just a step function that you talk about, right. So which means, which has this specific property, this delta t is constant in each sub interval, left closed, right open interval of this sub intervals that you are considering. So which means that it will be of this form. Just prior to t1, this will take this value which is in the lower one, and at t1 it will take the higher value, which is what is meant to this. Okay. So this is what will look like a simple path. So this path again, where the randomness comes in, because this path would depend on the omega that you pick. So this would depend on, for each omega you have one such path, and hence you have this as a simple process, right. Otherwise it's called simple function, but this is simple process because for each of this omega observation you can also make this first part will remain the same as long as T1 remain the same along any path because this is delta 0, right. So, that is what you would observe here. So, this is what is a simple process means. Okay. Now, let us look at the interplay. We think of the interplay between the delta t and Wt in the following way. Okay. Now, what we do is that just regard just regard this Wt as the price per share of some asset at time t. This is to give meaning to this, okay. Otherwise, it is just a mathematical construction, but you just regard so that we can associate a meaning to such a quantity that we are talking about here, okay. And like this will not be true in reality because Wt by definition is a normal random variable which can take any value between minus infinity to plus infinity, and associating this with the price of a particular share is not going to be a meaningful quantity, right, because it can take negatively Wt, whereas in reality the price is non-negative quantity. That is what you would see. So, this is just for our understanding purpose. So, regard this and delta t in a similar way, and this time points like t0, t1, t2 and so on, these are all you regard this as a trading dates, which means these are the dates or the time points at which you do make trade, and think of delta t0, delta t1 and so on, delta tn as the positions, right. We mean the number of shares that you hold, positions taken at each trading date, right, at each trading date, okay. Then if you regard the gain from trading, what is this quantity? If you regard, suppose if I call this as IT, okay, this will be simply because my position at the beginning is delta t0, t0 equal to 0, it is delta naught, then Wt minus Wt0, right, which is nothing but delta naught and Wt. This is true for all t less than or equal to t1, right, because I start holding the position of delta naught at time 0 and I buy the asset at the price W0, which is 0 here, and by time t this W0 would have grown to this Wt and my position is this, right. So, this difference is what is the difference, the appreciation that you gain by holding each of this share, and you are holding delta t0 number of shares. So, the total gain is delta naught times Wt, right. This is for t lies between this. Now, suppose if I take my t lies between say t1 and t2, then what would be this quantity? This quantity would be delta naught Wt1 until that the gain from 0 to t1 is this, plus at t1 I change my position to delta t1, and the difference in the price of the underlying asset between t1 and t for t lies between t1 and t2 would be given by this, right. So, this is what is the gain. So, this is the total gain, delta naught Wt1 is the gain that I have from 0 to t1. This is from t1, the second term is from t1 to t. Similarly, if my t2 less than or equal to t3, then this is delta naught WT1 plus delta T1 WT2 minus WT1, then again I change my position at T2 to delta T2 WT2 sorry WT minus WT2 is what is the right. So, this way you can see that you can extend for each of the intervals, right. If my t lies between this and this, then this is what is this IT, which is basically the gain from trading that this quantity, and if t lies between say T2 and T3, and you can extend in this way, you can define for all t between 0 to any value that you are thinking, right. So, in general, let us write a general expression. In general, if my t is lies between some Tk and Tk plus 1, then my IT, which is you can also remember that this could also be written as I of t, right. So, this is same as this. So, but we as we said, for simplicity we are writing in this form. This will be some j equal to 0 to k minus 1 of delta Tj WTj plus 1 minus WTj plus delta Tk Wt minus Wtk, right. And I would urge you to look at this quantity is what we will be interested to keep in mind as IT. So, this is what we call the Ito integral of the simple process delta t. So, this is basically, if you look at now, IT is not just one value, right, it is a process. Okay. So, this is what would be, right. So, this is what we write it as IT is what we write it as 0 to t delta u say dwu, and this is what is we call the Ito integral of a simple. So, what is the meaning of this? Okay. So, the meaning when we write when we write this quantity, okay, the meaning for delta u simple process is essentially given by this summation, that is what it is. Okay. This is for the simple integrand, okay. That is what we define. Now, we wanted to make sense of 0 to integral 0 to capital T delta u dwe, but we not just for one particular capital T we have defined for all t which lies between 0 and t what is the meaning of this, and that is what is given by this expression. And if you think of this upper limit of this integral as a variable, then you would get this as a process, which is what we call it as this Ito integral process. Okay. So, when we look at this is as a process, then we can look at its properties now. Some of the simple properties we can look at from the simple for the simple integrand case, right. Now, you have already know that W being Brownian motion is a martingale. Okay. Now, you are trading in a Brownian motion asset, sorry, in a martingale asset. Brownian motion, which is a martingale. So, you are trading in a martingale asset. Now, since martingales has no tendency to either rise or fall, if you trade in a martingale asset, what do you expect the gain? The gain also should be in such a way that it neither rise nor fall, right. And that is what is the first fact that we will give, that the Ito integral, the definition is we are given above. The Ito integral is essentially defined by star, okay, is a martingale, right. Okay. So, you keep this summation in mind, right. This is what is the meaning of this Ito integral for any t that we have. So, this is what we keep repeating, and hence we say this is what is important, you need to remember. Now, let us look at how do we prove this. Okay, let us do the simple proofs. Later, we will going to take the results for granted for any general Ito integral, but at least the meaning should be clear from the simple cases. Okay. Now, we will assume that S and T, so they are in different subintervals. Okay. Otherwise, what will happen? The following proof that we make will become simpler, that is the only thing. Okay. So, which means that what? So, say, there is this, so which means that there exists TL and TK such that okay, TL and TK with the condition that my TL is less than TK, and so these two are such that my S is in TL to TL plus 1 and TK, sorry, my T rather, T belongs to, because IT, S and T is what you have picked. So, T belongs to some TK plus 1. Okay. Now, my IT, I can write it in the following form. I can expand first from J to L minus 1 of WTJ, sorry, this should be delta Tj WTJ plus 1 minus WTJ, this is up to L. Then for the Lth interval, I can write this in this form, that WTL plus 1 minus WTL plus, now from L plus 1 to K minus 1, my delta Tj WTJ plus 1 minus WTJ, where J running from J plus 1 to K minus 1, and the last term here, which is delta Tk, is Wt minus Wtk, right. So, this is what is the term. There is first, second, third, fourth term here. Okay. So, let us call this as term 1, 2, 3 and 4. Okay. Now, look at one by one what happens in this case. So, what we have to show? So, to show is expectation of IT given Fs is Is, right. This is what we need to show. Now, let us look at these 4 terms that we have here and look at one by one. Okay. We have Fs, okay, and my S belongs to the interval TL to TL plus 1. So, the S belongs to TL to TL plus 1, and all the quantity terms which are there inside the first sum, okay, the first term, the inside quantities which is there in the first term, they are all you would see measurable with respect to Fs, because all of them are time before time TL, and TL is less than or equal to S. Okay, so all of them are Fs measurable. So basically what we have, so all the quantities, one, this is Fs measurable. Okay, so which means when I take this conditional interpretation, that is what you are observing. Okay, now for 2, if I take the conditional expectation, right. So we use the, so this is basically we have to take these two quantities. So we will take the conditional expectation, so Fs measurable. So basically now if I take the conditional expectation of the terms 1 given Fs would turn out to be the complete terms 1, right. So that is what we have here, the one that we have. So whatever you do, like with regard to the consideration of that given Fs, because this one is Fs measurable, so whatever you have, it will come to. As far as the second term is concerned, you can see delta TL WTL plus 1 minus WTL given Fs. Okay. Now you can see out of these terms, your WTL is Fs measurable. So you can take that out, and you can take the expectation inside, and you see WTL is again Fs measurable, whereas this quantity is not Fs measurable. So it will remain as it is. Expectation of WTL plus 1 given Fs minus WTL, right. So this is what you have it. But what is the quantity inside the bracket? What is the first quantity? Which says that expectation of WTL plus 1, where TL plus 1 is greater than or equal to S, the consideration of this quantity given Fs, and we know that W, which is the Brownian motion, is a martingale, right. So this quantity is nothing but WTL times Ws minus WTL. This is what will turn out to be the second quantity in the term here. Now you can easily observe that from this one and terms, two terms, we see that immediately this expectation of IT given Fs is nothing but Is. Okay. You can immediately see that this is true. So we will then have this as the result, which is what we wanted, but this would be true only if the other two terms that we have here, if they are 0, when you take conditional expectation of IT given Fs, the third term and fourth term must be 0, then only this is true. So let us see why, how, and the third term and fourth term are 0. Now for 3, for the third term, what you can do, you can just pick one of the terms and take the conditional expectation, and since when you take conditional expectation of the sum, it is the sum of the conditional expectation by linearity property, so the sum would follow. Okay. Now for the third term, consider the one term which is delta Tj Wtj plus 1 minus Wtj, right, given Fs. This is the one of the term. Remember here we have my Tj is greater than or equal to TL plus 1, which is greater than or equal to S. So that you need to remember. Okay. So this then means I can do this following. So, this will be equal to, first we will write and then you will see how this is equal, delta Tj W Tj plus 1 minus W Tj given F Tj and given Fs, right. My Tj are all greater than or equal to TL plus 1, which is greater than or equal to S. Okay. So, this is basically what we are using. We are using the tower property of the conditional expectation or the iterative conditioning property of the conditional expectation, where Ftj would be greater than or larger sigma field than Fs, right. So, this is what we are having. Okay. Now, if I take the inner quantity alone, okay, delta Tj is Ftj measurable, I can take that out and I can apply the previous idea, that is how exactly we used it. So, this will be delta Tj and this quantity would be expectation of W Tj plus 1 given Ftj minus W Tj, right, given Fs is what then you would get. But this quantity is nothing but WTJ, right. So, if this quantity, if this is WTJ, so then, so this quantity is essentially expectation of delta Tj W Tj by virtue of W being the martingale minus W Tj given Fs. So, this is 0. So, the individual terms are 0, the sum is 0, right. So, this implies 3 for 3, okay, for 3 the expectation of the terms 3 given Fs would be 0, and similarly for 4 exactly the same argument, you would see 4 given Fs would also be equal to 0, and hence the proof that IT is a martingale. This is the first result, okay. Because now we know that this is a martingale and I0 is going to be 0, implies expectation of IT is equal to 0 for all t greater than or equal to 0. Okay. Then variance of this process IT, it would then nothing but this quantity. Okay. This is, so what is the quantity, what is equal, this quantity is equal to, is what then we are going to see next, okay, which is what is called as Ito isometry property. So, what we have here is e to the power, this expectation of I square t is nothing but delta squared u du. Okay. So, this is what is the second result, which is giving exactly the variance of this Ito integral process. Okay. Since mean is 0 and this is variance, which is what then we are looking at it, that we have. Okay. Now, again this the idea of the proof will be along similar lines as the earlier one. To simplify, proof notation. So, to simplify the notation, we will use dj as w tj plus 1 minus w tj, right, for j is equal to 0 1 up to k minus 1 and dk as wt minus w Tk for j is equal to essentially k. Okay, so that's it is not a meaning. So that we can write IT as simply for convenience k delta Tj dj, and we can write now what is this IT square. IT squared as j is equal to 0 to k delta Tj square dj square plus summation 0 less than or equal to I less than j less than or equal to k, sorry, twice I can put because I less than or equal to j I am putting, delta Ti delta Tj di dj. Okay. Now one can show by observing the terms on the cross product terms, right. The cross terms are 0 if I take the expectation, right. Now what we want to compute is expectation of this, right. So expectation of this is what we wanted, and the expectation of this one, okay. So these terms are going to be 0. You can easily see, note that expectation of delta Ti delta Tj di dj, if I look at it, okay. So out of this delta Ti, delta Tj and di are Ftj measurable, and while the Brownian motion increment dj is independent of Ftj. So that gives us that this is equal to essentially delta Ti delta Tj di times expectation of Tj, which is going, this quantity expectation of dj is going to be 0. So this is 0. So all the this the complete, this whole term will be equal to 0, right. So because of this, so then the left out is only this. Now if I look at what is expectation of this quantity, expectation of IT square, then you would see that this is summation of delta, sorry, expectation of delta Tj square dj square is what then you have. Now again, by looking at these two quantities, these are independent. So you can look at this as expectation of delta square Tj and expectation of dj square, right, which is nothing but now summation expectation of Tj square, and that quantity is nothing but my Tj plus 1 minus Tj. Okay. So this is for, now I have to write a little bit more carefully. So this is j0 to k, j0 to k minus 1 plus for the final term, which is expectation of delta Tk square T minus Tk, that is what you will come, right. Now you know that delta Tj being simple integrand is constant in each of the sub interval, right. So you can use that and you can write, you can use that and you can write this quantity as the following, right. You have summation j to k minus 1 expectation of Tj to Tj plus 1 of delta square u du, right, because this is what is exactly would be equal to expectation of delta d square Tj minus 1 minus Tj if we put this. So we write in general in this form plus Tk to t. Okay. So, this expectation now I can even take it outside, tk to t delta square u du, which is nothing but now expectation of 0 to t delta square u du. This is what is the proof of the Ito isometry, which gives the variance of the things. Okay. So, we now turn to the third result, which is important also, is that the quadratic variation accumulated up to t by the Ito integral is given by this I of t. Again, this is a process, so we will just write it in this manner, delta square u du. Okay. Now, finally, you see that see, in case of simple Brownian motion, you saw the quadratic variation is also t and variance also t, but here you see the difference, that the variance is expectation of this quantity, whereas quadratic variation is this, because since it would vary from path to path. So, this quantity also will vary from path to path. Like if you take a larger positions delta u along one particular path, this quantity will be larger. If you take smaller values of delta u along another sample path, then this quantity is going to be smaller, whereas our variance is an expected measure which is going to be a constant. So, here really you see that this is what is happening. Okay. So, this again we can compute the quadratic variation accumulated. So, this proof idea, I mean we just give an idea about the proof. So, basically take Tj an interval, sub interval Tj to Tj plus 1, on which my delta u is constant, right, in that it is a constant. Now, you choose a partition points Tj is equal to some S naught less than S1 and so on less than Sm is equal to Tj plus 1. Now, consider this sum, right, I plus 1 minus I s I and then its square, right, which will turn out to be the constant, which is delta square Tj, and this is 0 to m minus 1 W s I plus 1 minus W s I the whole square, right. Now, as in the usual limiting process, which means as the norm of this partition of this sub interval tending to 0, that means as m tends to infinity and the norm of this partition tending to 0, this quantity, right. So, especially for example, if you look at this quantity, this converges to, right, as norm of this partition tending to 0, right, that is as m tends to infinity and the norm of partition tending to 0, this quantity converges to the quadratic variation of this W in this interval, which is again Tj plus 1 minus Tj, right. This is what you would see. So, what we see is that the quadratic variation in the sub interval, right, is essentially quadratic variation in the sub interval is delta square Tj plus 1 minus Tj, which you can write it as Tj to Tj plus 1 of delta square u du. Now, for full 0 to t, you will get it sum these quantities, right. So, that is the idea of the proof that you would get. So, for once you find this for the sub interval, then you will get the overall quadratic variation which proves the result, right. So, finally, what you have seen is that the three basic properties of the Ito integral, which is martingale property, Ito isometry property and the quadratic variation property of what you have seen. Okay. So, now recall that earlier the bread and butter expressions for the quadratic variation, the informal way of writing is this, right. Okay. So, this is what we write informally to mean this. Remember, this is informal way, this is a square bracket is a formal way of writing this, right. Now, the Ito integral which is this delta u dwu can be written as informal way as dit as delta t dwt. Okay. Now, what we can write for the quadratic variation of I, we can take this quantity which is essentially delta t square dwt if I use dit as this. Now, if I use dwt as dt as given by that, so this is delta t square dt, right. This is what is the meaning that the Ito integral accumulates quadratic variation at the rate delta t squared per unit of time, right. So, the rate of accumulation is what is given. This is what is the previous result you would have in the pen and paper calculation to easily understand and see what is this quantity, you can also look at in this manner. Okay. Now, for the notation which we will be using this pen and paper calculation, this kind of differential form rather than the integral form. So, we can see that this notation as we wrote earlier, this is IT is basically 0 to t delta u dwu and dit is delta t dwt. They mean almost the same thing, but the first one has a precise meaning, the second one does not have a precise meaning, it is just that, but second one is more intuitive what is happening to I, okay, which means the change in I can be given in terms of delta t times the change in W. So, it has that informal meaning of what happens, whereas its precise definition is given by as in the first one, right. That is what, and second one has an imprecise meaning as we just described. Okay. It also has a precise meaning which one obtains by integrating this differential over both sides over an integral and put in a constant. So, it is basically I of t, you can also write I0 plus 0 to t delta u dwu, right. So, this is basically the differential form, and this will be called as the integral form. The difference between the first one and the third one is that you have a constant I0 generic constant here, and then here it is I0 is assumed to be 0. Okay. So, you can write that in the differential form in this means with the assumption that I0 is 0, then it becomes the second one. But the second one for any generic one has the meaning, the integral form is given by. So, this is a differential form and integral form. Whenever we have a process we describe in terms of the differential form, we should also understand that the corresponding the precise meaning is in terms of the integral form that we have in the third quantity here into this case, right. So, this is what is all about the Ito integral for simple integrand. Now let us define the Ito's integral for general integrands. Okay. So what we have is now a general integrand, but we need to put some condition. So what is the condition that we assume that will follow throughout is essentially, we have the general integrand is adapted, that is clear, adapted to this ft just like the simple integrand case, and we also assume what we call the square integrability condition. Okay. This is expectation of 0 to t delta squared t dt is finite. Okay. This is what is the square integrability condition. In fact, one can define an Ito integral with respect to a condition which is weaker than this, that is without this expectation, but in that case the expectation is not guaranteed to be a martingale, and since in our things we consider only such cases. In our case, Ito integral, all Ito integrals will be martingale. So that requires that square integrability condition be imposed. So this is what is the square integrability condition of this process that we have here. Okay. Now how do we get for a general integrand the Ito integral? Okay. So what we do is that we approximate this given delta t by a simple process, and then we make this approximation finer and finer at the maximal step size of the partition approaches 0. The approximate integral will be better approximation in some sense. So essentially what we are looking at, if I depict graphically in a simple manner, so what I have is this, the given process could be something like this. So it is coming up to that point, and then from here then again it goes like this. Now so this is the general delta t. Now how does the simple process will look like? Suppose the simple process might up to this it might come. So this is my first partition point, and at this point it will take this particular value and it will continue up to certain point, and at this point again, suppose if this is my second point T2, at this point it is starting from here, it will take up to say this value, and this is my T3, this is my T1, and at this point then this will be equal to this, and at this point say this is my T4, it is this value and it will be equal to this. Right. This dotted lines is what is the simple integrand, this straight line is what is the general integrand. We will try to take such approximations, and then we take this approximation, make but finer and finer. So it is basically, so it is it is possible. So in general it is possible to choose a sequence delta n of t of simple processes, okay, of simple processes such that as n tends to infinity, these processes, okay, these simple processes converge to delta t by, in the sense that limit n tends to infinity of expectation 0 to t of delta n t minus delta t square dt is 0, right. So this is what we mean when we say things converge. Okay. Now, since each of these are all simple process, okay. For each one of these we can define delta n of u dwu, okay. So, this can be defined. So, this can be defined as earlier, right. Now, for each simple process this thing can be defined, right. Then we define the Ito integral of the general process to be the limit. We define the Ito integral to be 0 to t delta n of u dw of u. For each of this simple process delta n, you can compute the quantity, and the limit of that as n tends to infinity is what then we define to be the Ito integral of the general quantity that we have here, right. Now, let us look at its properties, the Ito integrals general properties, okay. So, we have a a positive constant, I mean an interval, say 0 to t is what you are looking at it, and you have an adapted process, okay, and you define IT as above as a limit of Ito integrals of simple integrands. Then the properties are A. The first one is continuity property, which says the following: as a function of the upper limit of integration t, the paths of IT are continuous, essentially meaning that this IT has continuous paths. B, adaptivity, which means that for each t, IT is Ft measurable. C, again the linearity property of this integral, if my IT is some 0 to t delta u dwu and Jt is 0 to t some gamma u dwu, then IT plus or minus some C times Jt is essentially would be equal to 0 to t delta u plus or minus C times gamma u dw, and for a constant C. Okay. This is the linearity property. Then this is in fact you can also see with respect to the simple integrand, these are also true. Then the properties that we proved for simple integrand and which is inherited by this limiting process. This is a martingale. E, Ito isometry, property, which is expectation of this IT square is expectation of 0 to t delta u square du, and f quadratic variation, which is I of t is essentially 0 to t delta square u du. So, all these are properties of this Ito integral, which we will use elsewhere too, and these properties, of course, now Martingale isometric quadratic variation property we are not going to prove, and but this is what would be the case. Okay. Let us take a simple example to understand, to close the discussion of this. So, what we can do look at is 0 to t Wt dWt is what then we want to do. Okay. So, what is this quantity is and from where this is coming, right. Now, this you can define, okay, or this one. So, what we have to do now, how do we have to compute if we have to apply the basic principles, that we have to define this quantity by in terms of limit of integrals of some simple integrands which approximates Wt. Okay. So, what is the approximation? The approximation here is, suppose if I look at here, I can take this to be W0 if my t lies between this. This will be W okay, capital T by n if t by n less than or equal to t less than 2 t by n, and so on. Okay. And so on, I will have the last one as n minus 1 t by n if my t n minus 1 by t1 less than or equal to t less than capital T. Okay. So, if I take this to be the case, this to be the approximating simple integrands, then we can write this as 0 to t dWt as limit n tends to infinity of 0 to t delta n t dWt, right, which is nothing but limit n tends to infinity of summation j is equal to 0 to n minus 1 W j t by n W j plus 1 t by n minus W j t by n, right. This is the quantity that you have here. Okay. Remember now what we are doing, we are taking the interval 0 to t and we are partitioning into equally spaced sub intervals of length t by n, and on each of these intervals we are taking the approximation to Wt as the point at the leftmost point at the interval. So, that in that sub interval this adaptedness or the of the delta nt is ensured, right. So, this is, as we saw, I mean the interpretation which we could give is this is essentially the position that you are taking. So, essentially for some interval you are assuming that the positions you are taking is at the beginning of the interval, that you are going to make it constant or remain constant for that particular interval. Okay. Now, one can, by simple algebraic manipulation, okay, one can show that the quantity, the sum that we have here n minus 1 W j t by n as W j plus 1 t by n minus w j sorry j t by n is equals half w squared t minus half summation j is equal to 0 to n minus 1 w j plus 1 t by n minus w j t by n the whole square. So, what you can do is that you can consider the quantity in the right hand side, this summation, and you can try to express this in terms of some algebraic manipulation. If you do, you can show that this quantity is equal to this. Okay. Now, if you let the limit tends to, so because this quantity now you have said that this is equal to this, right, to the right hand side. Now, this right hand side quantity, right, you can see that this tends to half, right, w square t minus half of w of t as n tends to infinity. Okay. This is equal to again, so this is equal to half w square t minus this one w of t is you know as t, right. So, because this is the quadratic variation of this w. So, essentially what you have shown that integral 0 to t w t dwt is nothing but half w square minus half t. Okay. Now, contrast this with your ordinary calculus where this w, suppose if for some function g which is a differentiable function with g of 0 equal to 0, you will see that this will be only the first term on the right hand side is what then you would get, right. And the second term is from where this is coming? It is because of the positive quadratic variation that the Brownian motion paths have, and as you see this w half times t is essentially is coming from the quadratic variation of this w. So, that is what gives rise to this term, and this is true for the case when you have the integrals defined in the Ito's way. So, this is basically due to quadratic variation. If this is not the case in the ordinary calculus where wt, I mean generally if you take to be differentiable function, then you will see 0 to t gt dgt is equal to half times gt square, that is what you would get. But here this minus half terms t is essentially this coming from the quadratic variation term, right. So, since this upper limit can be arbitrary, so we can define or we can write this w dwu to be half of w square t minus half of t for any t greater than or equal to 0, right. So, we know, and now we know like from where this is coming. So, this is you can write this as half of w t square minus t, you can also see that from where this is coming. So, this is to be martingale, and for this martingale this is quantity is nothing but same as this, and the right hand side we already know that this is a martingale. So, the left hand side also need to be a martingale. So, to make this case then you are actually expectation of w t squared is equal to t. So, this quantity is going to be 0 in expectation, and this is what is the case. So, this is an example that you can see which comes, and this is what is the difference between the ordinary calculus and stochastic calculus, that the quadratic variation of the Brownian motion plays a crucial role in determining what is these quantities are equal, whereas this might vanish even. It is not in the this is true only with respect to Ito's integral, where you are evaluating the for function at the leftmost point, otherwise even this minus half times t may not appear. It is not true for in general for a stochastic integral, but it is true for an Ito integral. That is what we have it here. Okay. So, this is what is all about the Ito integral and its properties, and when we in the next lecture we will talk about the Ito's formula. Thank you. Bye.